use change of variables or general substitution. I'm going to be using those terms interchangeably to integrate f of xy as y squared plus xy over the region in the first quadrant given by these bounds here. So if you want to graph the region here, it ends up looking like this. And I guess that's the region that we're going. It would be a mess to try to integrate this in the xy plane. So we want to try to think about a map here from the UV plane where it's coming from, a relatively nice region in the UV plane. What should we choose for u and v? Well, take a look here. 1 is less than or equal to the square root of x times y is less than or equal to 4. 1 is less than or equal to the square root of y over x is less than or equal to 4. I think that this really suggests, again, thinking that in the UV plane the bounds should be nice. If we call this whole thing u, and we call this whole thing v, so u is equal to square root of x times y, v is equal to square root of y over x here, then these bounds become u is between 1 and 4, v is also between 1 and 4, and we can integrate in the UV plane 1 to 4, 1 to 4. We're integrating over this square instead, and our life is a lot easier. So instead of integrating over r, we're going to integrate over g, and this makes our life a lot easier. Okay, so we know this is how we're aiming. We know what our change of variables is going to be, except that we have the change of variables. We have u in terms of x and y, v in terms of x and y. We want x and y in terms of u and v. So how do we get that? Well, first thing observe is that if we multiply together u times v, u is square root of xy, v is square root of y over x. So this is the square root of x times y over x. The x's cancel. The square root of y squared is just y. Everything in sight, we're in the first quadrant, everything in sight in positive, so we can just square root of y squared is y. So y is equal to u times v. Now how about for x here? Something that we can realize is that if we do u divided by v, let's try u divided by v, square root of xy over square root of y over x here. And so what happens here? This is going to be a square root of xy over y over x. The y's cancel, and we get the square root of x squared, which is x. Again, first quadrant, everything is positive. So our map, x is equal to u over v, y is equal to u times v. This is our transformation here. What is our Jacobian in terms of uv? Okay, the x partial derivative with respect to u is going to be 1 over v. Partial derivative with respect to v is negative u over v squared. The partial derivative of y with respect to u is v. The partial derivative of y with respect to v is u. And so we end up with 1 over v times u. That's u over v minus u over v squared minus negative u over v squared times v. This is u over v plus u over v to u over v. So what does this tell us? Okay, the double integral over r of y squared plus xy dA is equal to the integral u runs from 1 to 4, v runs from 1 to 4 of y squared plus xy. Okay, we need to introduce here y squared is uv quantity squared plus x times y u over v times uv times the absolute value of 2u over v. Absolute value of 2u over v, everything inside is positive, so it's just 2u over v dv du. Okay, so u from 1 to 4, v from 1 to 4 of, let's see here, we should end up with 2u cubed v plus 2u cubed, and then v over v squared over v dv du. Okay, so this is where we're at. I'm going to stop working this out here. Relatively straightforward integration at this point. The interesting part is coming up with the appropriate change of variables, identifying what u and v are, going from that to figure out what x and y are in terms of u and v.